Hello, so today we're going to talk about how to evaluate a limit using algebra. These are different algebra skills. Last time we talked about using a graph and the numerical evaluation. And again, of those two methods, graphing is a very reliable method to use, and I do recommend it if obviously the graph is given to you, or if you have the use of a graphing calculator. Now, again, not all questions will allow you to do that. That's why you need to remember how to use your algebra skills. And for the most part, to evaluate a limit analytically, it's very simple. You just plug in the given x value into the function. As we discussed last time, most times the limit and the value are the exact same thing. So by plugging it in, you get the value and the limit, and you're okay. Now, there are some cases where this will not work. If you get 0 divided by 0, this is what we call an indeterminate limit, because you can't have 0 divided by 0. Divided by 0 makes no sense. Doing 0 divided by 0 makes even less sense. In this particular case, which we will explore, there are different ways you're going to have to evaluate these limits, different types of functions you're going to have to work with. Now, if you get 3 divided by 0, that's fine. That's a does not exist limit, because you can't divide by 0. If you have 0 divided by 3, that's also fine, because that's 0. No big deal. But if you get 0 over 0, that's a special type of limit, and we will discuss how to deal with that. But in general, you just plug in. So if I want to find the limit as x approaches 2 of x cubed, we just plug in 2 for x, and we get 8. It's that simple. It's that straightforward. Most limits really are that easy, and that's what you always really want to go with in the first bet. Even when we talk about different types of problems that will be 0 over 0, you still want to always plug in first. Because just because it looks like something you've seen that would be a 0 over 0, doesn't mean it has to always be that way. So it's always best to plug in first. So in this case, you plug in 0 for x, and we get negative 1. Pretty easy. 2 times 0 is 0. 0 minus 1, negative 1. We plug in negative 3. Be careful with the negative since you're squaring. So when we square the negative, we get positive 9. And we get 0. Again, very straightforward. So why don't you go ahead and plug in negative 4 on your own. Make sure you get your answer. This should take you no longer than a couple seconds. So I'll go ahead and pause the video while you work that out. Okay, you should be getting a positive 17 for this particular limit. Now, one thing about limits that may either annoy you or whatever is sometimes you're going to be dealing with trig limits. Now, again, it's a simple plug-in, not a big deal at all. But for the most part, problems like this problem right here are not going to be will be on the AP test that won't let you use a calculator, which means you need to remember unit circle and have it memorized. If you know how to create the unit circle, again, from memory, that's fine. No big deal to go ahead and just create that. Remember your 1, 2, 3, 3, 2, 1 method to create the different boxes and how they're all the same. But that's tedious. That'll waste you a good couple minutes that you really need to use to solve other harder problems, and this should be very straightforward. So you need to remember, for example, that sine of pi over 2 is 1. Cosine of pi over 2 is 0. Stuff like, cosine of 5 pi over 6 is a negative square root of 3 over 2. Stuff like that. You need to make sure you have it memorized so that it takes you no longer than a couple seconds to recall the information. So here we have cosine of pi x over 3 when x approaches 1. So if x is 1, this becomes cosine of pi over 3. We should remember cosine of pi over 3 is equal to 1/2. Also, though, when you are allowed to use a calculator, feel free to do in this case. For the most part, you're going to need to be in radians for the AP Calc test. So if you're taking a class like physics, which generally requires you to be in degrees, you need to make sure you're careful and switch back and forth appropriately. Again, with other trig functions, you'll have to remember how to work how secant, cosecant, and cotangent works. So secant is really 1 over cosine, so this becomes 1 over cosine of 2 times 0, which is 0. Cosine of 0 is 1. 1 divided by 1 is 1. So you have to remember all that kind of stuff. Now, those are your very straightforward ones. You just simply plug in, getting the number you get out. There are 3 different types of problems, though, that when you plug in, you will get 0 over 0. And we need to talk about how to answer these questions. And you have to use your algebra skills to manipulate them. There is another method which we will talk about at the end of this unit. It technically requires knowledge of derivatives, which we'll talk about again later on as well. So, but for right now, you have to use our dividing out technique, rationalizing, or combining fractions. And we'll see what these problems look like. So for example, we have this. The limit as x approaches 4 of x minus 4 over x squared minus 16. And again, like always, we should always plug in first and see what happens. And we do get 0 over 0. When we plug in 4, we get 0 over 0. Now, in this case, because we're dealing with polynomial functions, the key for this is our dividing out technique. We want to factor the top part of the expression and the bottom part of the expression as far as possible. Because after factoring it, if we have 0 over 0, we should know something does cancel out. So x minus 4 doesn't do anything, but x squared minus 16 is a perfect square, difference of two squares. So it becomes x plus 4 and x minus 4. The square root of 16 is 4, that's why those numbers are 4. Well, as you can see, we have x minus 4s, so this really becomes 1 over x plus 4. So that means this limit right here is the equivalent to find the limit as x approaches 4 of 1 over x plus 4. This now becomes so much easier because now we plug in 4 for x, we get an answer of 1/8. So that's how the dividing out technique works. If we notice we have 0 over 0 and we have polynomials, we factor and cancel them out. You've seen this before in your pre-calc class. This right here is an example of a whole. If we were to try and graph this original function, x minus 4 over x squared minus 16, there would be a whole when x equals 4 at the y value of 1/8. You've already done this. And you actually will find a lot of different techniques here, and a lot of different things with calculus you've seen before in a different context in your pre-calculus class. There's a method behind the madness of how we teach you. It's not just all random. So I want you to go ahead and do this one on your own. You should notice when we plug in, you get 0 over 0, and that's fine. This is our indeterminate form. You want to divide them out. So you're going to factor both those quadratics, and you should find an expression cancels, and then evaluate again. So I'll go ahead and pause the video now while you work on that. Okay, so when we factor this, we notice we had x plus 3's in both the top and bottom expressions, so they cancel out, leaving just x minus 2 over x minus 3. From there, we now plug in the negative 3 in for x. We get negative 5 over negative 6, which is a positive 5/6. So that's what you can do when the problems look like this. You have 0 over 0 and you plug in for your limit. If they're both polynomial functions, factor and cancel. Now, square root functions are going to be a little bit different. So again, if we plug in first, plug in 4 for x, we are still going to get our 0 over 0, because that's what all these problems are going to be. Now in this case, because we have a square root function, we're going to use our rationalization technique. Now you've done something like this before. For example, if you had something like this, in a problem, you couldn't leave it like that. So you weren't allowed to leave a square root in the denominator. So you rationalize it by multiplying top and bottom by the conjugate, the square root of 3 plus 1. That cancels out the square root and put it in the right spots. Here we're going to use that same idea. We're going to multiply top and bottom by the conjugate of the square root so that I can cancel the square root from up top. And you might be thinking, well, how is that going to help me? That's going to move the square root to the bottom. Trust me, something nice happens for these particular problems. We have the square root of x plus 5 minus 3 over x minus 4. We multiply by the square root of x plus 5 plus 3 on top and bottom. Again, the conjugate. So the only thing that changes is the sign in between the square root and the other number. Now, the reason why I multiply by the conjugate is it eliminates the square root from where it is. Because notice we are multiplying by two binomials that just have a difference in the middle. So this really is equivalent to this situation right here. Our a minus b times a plus b always worked out to just be a squared minus b squared. No middle term. So if I square the first term, we get rid of the square and just left with x plus 5. And then minus, if I square the second term, I get 9. It doesn't do me any good to multiply out the bottom, so I'm just going to leave it alone. And this is going to become very apparent in a second. Because when I combine like terms up top, 5 minus 9 is negative 4. And lo and behold, we notice we have an x minus 4 expression, now both on top and bottom, meaning they cancel, leaving just 1 over the conjugate expression, square root of x plus 5 plus 3. Now when I plug in 4 for x, I'm no longer going to get 0 over 0. Now I'm going to get a much nicer term. I am going to get 1/6 for this particular problem. So that's what the rationalization technique is going to do. It allows us to get rid of the square root up top, but it really allows us to actually find a way to cancel both top and bottom. It's one of the nice things about how this works. It is guaranteed to cancel something if you have 0 over 0 and you have the square root for your rationalization technique. It has to work out. It's just one of the ways it works. Don't ask me to explain the exact reason why. It happens to work every single time. Mathematically, it makes sense. I'm sure someone smarter than me could fully explain it. Again, the nice thing that generally comes out of this, for the most part, is all that's left over is either 1 over the conjugate if the square is up top, or the conjugate over 1 if the square is on the bottom. There may be some other numbers involved in some very rare cases, but for the most part, just 1 over the conjugate, or the conjugate over 1. Okay? Now, why don't you go ahead and take a look at this one right here. Again, it's the same concept. If you plug in 0 right now, and go ahead and do that when you do this on your own, you will find it's 0 over 0. So what you'll want to do is multiply top and bottom by the conjugate of the expression, and that will find that it cancels something out with the bottom. So then work that out and get your answer. I'll pause the video and then show you my work in a second. Okay, so for this example, you should be getting the square root of 5 over 10 for your final answer. Again, if we multiply the top and bottom by the conjugate, the square root of x plus 5 plus square root of 5, again, it's in the form of a minus b times a plus b. So all we do is just square the first and last terms and put a minus sign between. When you square your square root, it goes away, leaving just the inside. That's why it's just x plus 5 minus 5. The bottom, again, we don't want to distribute the expressions together because things should cancel. Well, up top, the 5's cancel, leaving just x. The x's will cancel out, leaving just 1 over the conjugates, as I predicted. When we now plug in 0 for x, we get 1 over square root of 0 plus 5 plus square root of 5, which become 1 over square root of 5 plus square root of 5. Since those are both like terms, they combine to be 2 square root of 5. Again, it's kind of like x plus x is 2x. As we know from our work in Algebra 1, we can't leave a square root in the denominator, which is why we multiply top and bottom by the square root of 5 to rationalize it out. That's why we get square root of 5 over 2 times 5, because the square roots cancel. 2 times 5 is 10, which is why the final answer is the square root of 5 over 10. Okay, so that's your rationalization technique. Now, the last type of common problem you're going to see involving your algebra skills is when you have fractions. Or again, if I plug in 0 for x, you get 1/3 minus 1/3 up top, which is just 0. And again, we can't have this. Now, what we need to do is, when we work with fractions inside fractions like this, is we need to combine the top two different fractions into one fraction. So we need to subtract these two, combine into one. Well, remember, when we subtract fractions, or when we add them, they must have a common denominator. X plus 3 and 3 are not common, so one easy way to do it is to make sure they have the same denominator. So this needs a 3, so I'm going to multiply this top bottom by 3. This needs the expression x plus 3, so I'll multiply top bottom by that. That means we get this fraction 3 over 3 times x plus 3 minus x plus 3 over 3 times x plus 3. Now that I have the same denominators, I can subtract. So variables first, I'll have a negative x up top. 3 minus 3 cancels. So just negative x over 3, and I'll do a 3x plus now. I'll distribute it out. This is all over x. Well, again, I can't have a fraction inside a fraction, so I need to work on this. So, divided by x is the same thing as multiplying by the reciprocal. Again, remembering the rules with fractions, dividing fractions is equivalent to multiplying reciprocals. So we have our top negative x over 3x plus 9, now times 1 over x. Well, the x's cancel, leaving just negative 1 over 3x plus 9. And now we can plug in and get an answer. So when we have work with fractions like this, when we combine them to 1, the whole goal is to get down to a single fraction. You cannot have a fraction side fractions. You'll find something will cancel to allow you to not get 0 over 0. Because now when I plug in 0 for x, we just simply get negative 1/9. That's all there is to this particular problem. Okay. Again, like I said, the key is, as always with fractions, with any type of problem, whether it's an algebra, basic algebra, or more complex calculus, you got to get down to a single fraction. So that's why we went through this whole technique of combining the top fractions into 1, recognizing dividing by expression is the same thing as multiplying by the reciprocal, allows us to cancel. Once things cancel, we can plug in. And that's the same for all the other rules. For your rationalization technique, notice, we didn't plug in until after things canceled. We're dividing out. We didn't plug things until after things canceled. You must cancel something first before you can actually plug in. In this particular step here, none of this is canceling it. We're just combining stuff. It's only at here when things cancel that we can plug in. Now this right here is very important for concepts of derivatives. So let's talk about this. This delta x right here is not two separate variables. This is one variable. Think of delta x as equivalent to y. Delta me is the Greek letter, or delta right there is a Greek letter. In mathematics it means change. So this is really the change in x. So as the change in x approaches 0, is saying the x is getting smaller and smaller and smaller until pretty much the change is almost non-existent. We have this expression. And if we're plugging 0 right now, you will get 0 over 0. Because we'll just have x squared minus 2x plus 1, canceling there, and have 0 on the bottom. So for this particular problem, what we want to do is we want to square out this expression, combine like terms, and see what happens. Now remember, we have x plus delta x squared. It's really x plus delta x times x plus delta x. We've got to make sure we FOIL. So we get x squared plus 2x delta x plus delta x squared. And then minus 2x minus 2 delta x plus 1 minus x squared plus 2x minus 1, all divided by delta x. Again, these first three terms right here are from when we FOIL this out. So we get x squared plus delta x plus x delta x plus delta x squared. Again, I can't combine this x with this delta x because it's a separate variable. Think of, again, the delta x is y. Well, now something nice happens. Positive x squared, negative x squared. Cancel. Negative 2x, positive 2x. Positive 1, negative 1. Everything that does not have a delta x are actually going to cancel out with each other, leaving only delta x terms. 2x delta x plus delta x squared minus 2 delta x, all divided by delta x. And I notice that, wait a minute, I have delta x everywhere up top. So I can cancel one of my delta x's in each expression with a delta x in the bottom, leaving just 2x plus delta x minus 2. I plug in 0 for delta x, I just get 2x minus 2. This, we'll find out later on, is what we call the formal definition of a derivative of a function, where the function in this particular problem is x squared minus 2x plus 1. We will talk about how to work with that again in the next units. But there's just a little preview for what you're going to see. You're going to see delta x's a lot. Think of it as a separate variable, and don't get it confused with other x's. Okay? You'll find really for the most parts that most of the problems really here in limits, and actually in most of calculus, involve algebra manipulation. As long as your algebra skills are fine, you're going to be fine. Squeeze theorem. So what the squeeze theorem is saying is we have these three functions, h of x, f of x, and g of x. We define that h of x is the smallest, f of x is the middle, and g of x is the biggest. It's in between, f is in between h and g. Now let's say f of x is a function that we really can't evaluate on our own. We have no idea how to actually get the answer. But h of x and g of x are both known values. They both equal L. Well, if the value of h is L, and the value of g is also L, well, that's the same number. That means the middle term has to exist and it has to equal L. Because I can't be a number that's bigger than L, because again, fx has to be bigger than L, but it has to be less than L. So therefore it must equal L. This is what we call our squeeze theorem. It is one neat little way to force us to evaluate functions. And there are two special trig limits that come from this. There are proofs in this. You are more than welcome to look in your textbook for the proofs of these things. I'm not going to spend time doing this right now. But it turns out the limit as x approaches 0 of sine of x over x is equal to 1. The limit as x approaches 0 of 1 minus cosine of x over x is equal to 0. Again, there's different mathematical reasons for why this is true. We will actually talk about a technique later on that allows you to prove this very easily. But for right now, trust me when I say that these values are 1 and 0. And the key is for these kind of problems is you're going to see these things hidden in future problems. For example, if we have the limit of x approaches 0 of sine of x over 5x, this is very similar to what we just saw. The limit as x approaches 0 of sine of x over x, which was 1. Notice, this right here is our sine of x over x. So I can really separate this as 5 times the limit as x approaches 0 of sine of x over x. Well, this right here is 1. We get 5 times 1, which is 5. And that's how we're going to use these special trig limits. We're going to see where they appear in the problem and separate out so that it can work out exactly like that. For example, this one right here, we have sine of x times 1 minus cosine of x over x squared. Well, if you think of x squared as just simply x times x, I can separate it out. Well, the first half is sine of x over x, which I know that limit is 1. And the second half is 1 minus cosine of x over x, which I know that limit is 0. 1 times 0 is just simply 0. Again, we are separating out the trig limits. So why don't you see if you can separate out this trig limit right here so you can actually evaluate the problem. The limit as x approaches 0 of sine squared of x over x. So I will pause the video while you work on this. So as you can see for this particular example, we want to separate sine squared as two separate sine functions. Or I'll put one of them over x, and the other one is just kind of by itself. So sine of x over x times sine of x. Well, we know sine of x over x is equal to 1. And now if I plug in 0 for x, we get sine of 0. Well, sine of 0 is 0, according to our unit circle. 1 times 0 is then also 0. Okay, so those are your different algebra problems. I know this was a longer video than most of them. It's just simply because there are more examples to talk about. That's the key. There is, for the most part, they are very straightforward, but there are different ways of doing it, so you have to be careful. Again, the keys are always plug in first and see what happens, and if you're dealing with trig, you have to make sure you remember your different trig, your unit circle to plug in. Now, if you're plugging in like sine of like pi over 10, you're not going to have to use a unit circle for that because it doesn't exist on the unit circle. You will be allowed to calculate for that particular kind of problem. Okay, so that's it for this thing right here. We're going to talk about different special types of limits later on. So I will see you next time.